QuickTime's on. Now let's add Craig as well. All right, we're good. Let's get started then with Chapter 11, Electromagnetic Induction. So part 1 is electromagnetic induction. So when you have a conductor that's moved through a magnetic field, the delocalized electrons present in the conductor move towards one end of the conductor. Now this separation in charge causes a potential difference, and this generates a current. And this current is called an induced current. So let's look at an example of this, just to check if it works. Yep. So let's say we have a magnetic field over here that's pointing out of our whiteboard. Just draw a few. Yep. And let's say we have our conductor over here, this piece over here, which we move across in this direction. So we have a magnetic field that's pointing towards us or coming out of the board, and we have a conductor over here that's being moved through to the right, or at least what's to my right. Now, if you remember from chapter 5, we said that if we had an electron moving in a magnetic field, it would experience a force. And you could use Fleming's left-hand rule in order to figure that out, in which direction does the force act. So let's try use Fleming's left-hand rule over here to determine in which direction will our electrons move over here. So we have our magnetic field coming out of the board, so we put our index finger in that direction, and then we point our middle finger towards the way we're moving our conductor. So the resultant force causes all of our electrons to move downwards. So you have a partial negative charge over here, and you have a partial positive charge over here. This potential difference is what leads to a current being generated. And the potential difference generated over here is called induced EMF or motional EMF. Now the formula to calculate the induced EMF or the motional EMF is motional EMF equals to BVL. Let's write it down over here. The motional EMF equals to BVL. That's the motional EMF. This is our magnetic field strength. This is the speed at which our electrons are moving or our conductor is moving. And the length is how long the conductor is. Now we can have something similar happen in case of a solenoid. So let's say we have now, let's get rid of all of this, and we have a solenoid, which would look something like this if I were to draw it. So our coils, and let's just connect it to, let's say, an ammeter, so that we can see whether there's a current being generated or not. And let's say we have a magnet over here that we are moving towards our solenoid. Once again, you'll have a current being induced over here, and the direction in which our current will be induced, I believe, should be, well, let's just say we're moving it up and down constantly. So our current will be going like that and like that. It will keep flipping depending on the direction in which our magnet is moving. Note, our current will only be induced in case where we have our magnet is in motion or our coils or the conductor is in motion, because that's the only way the force would be exerted on the electrons, creating our motional EMF. So now in a case with solenoids like this, the magnetic flux, or the strength of our magnetic field, is given by, that's the symbol, it's given by NBA cos theta. So n is the number of coils that we have. In this case, it's 1, 2, 3, 4, 4 coils. B is the strength of the magnetic field that's coming from here. Then A is our cross-sectional area, so the cross-sectional area of a singular coil. And theta is the angle to the normal in which the motion is occurring. So let's draw a normal to our coil. And if our magnet, let's say, is moving in this direction, that angle there would be theta. So like that, you can see if we're doing it straight down, it's maximum cos, giving us the maximum magnetic flux, or it can also be called as flux linkage. Next, we have Faraday's law. Faraday's law states that the induced EMF is equal to the negative rate of change of magnetic flux. So what this means is the strength, or how large of an EMF that is being generated in our induced current or in our solenoid or our conductor, is entirely dependent on the rate at which the magnetic flux that the coil experiences changes. So motional EMF equals to negative n theta rate of change of our flux linkage, our magnetic flux. And n is once again our number of coils. Well, why does flux linkage change as we keep moving it? Well, you can think about it in this way. Let's say our magnet was initially over here. And let's draw our field lines. So we have a field that's running like this. We have a field that's, let's say, going like this. And we have a field that's coming all the way down here. Once again, going to the back. And so on like that. As you can see over here, the density of the field lines at our solenoid is quite less. So we have a weaker flux over here. But as we move our magnet to, let's say, over here, you'll have a lot more field lines that intersect with our solenoid, because of which it's stronger as you move it closer. And also, our flux linkage actually changes because you have a stronger magnetic field. And yeah, it's always related to the negative. So if our flux is increasing, then our motional EMF is getting more negative. If our flux is decreasing, it's getting less negative, or actually or more positive. And last, we have Lenz's law. So Lenz's law states that the induced EMF will be in such a direction that it will oppose the change in magnetic flux that created the current. So let's look at this in a simpler way. So let's say we have a loop over here, a conductor that's in a loop. And let's say we have a magnet that's falling down. It's a demonstration that we see quite often. We see it with a tube, a metal tube, or just a simple coil in this case, just to make things a little simple. So let's say this is moving down, and as it's falling down towards our coil, it's experiencing a changing magnetic flux. And by Faraday's law, we will get an induced current in this coil. But in what direction would this current be induced? So in order to find that, as our Lenz's law states that it will oppose the change in magnetic flux that created the current. So if you remember, once again, going back to chapter 5, when we have a current in a wire, it has a magnetic field around it. So we can use our right-hand grip rule in order to figure out the direction of current, the current direction, which will result in a north pole facing upwards. As opposite poles repel, it will oppose this motion. And our current will be induced in this direction. And now let's say if we had the opposite happening over here, and our magnet is falling with our south side down, it's falling down. Our current will be induced in the opposite direction such that our north is facing downwards. Thus our south will be upwards and it will oppose the magnet that's falling down. Which is why if you see any Lenz's law demonstration, when they drop a magnet, let's say through a metal tube, it'll fall slower once it's inside that tube, because you have such a magnetic field being generated by the induced current. And that is all for 11.1. Are there any questions before I move on to 11.2, which is transmission of power? When will these be uploaded to the revision website? Well, I'll try get them up by tomorrow night. I'm sorry for delaying it this much, but by tomorrow night it should be up. I really need to go through all of them and just make sure that it's good enough to upload. And don't worry, I will pin my channel over here when I upload it to YouTube, and it should be on the website as well. Any other question maybe related to 11.1? Or should I just go ahead? All right, cool. Let's move on to the next part, 11.2, transmission of power. What is an AC generator? AC generator, or alternating current generator, produces electricity using a coil and a magnetic field. So once again, our moving magnet scenario, except it does look a little bit different. You don't need to really know the functioning of an AC generator. We just need to know that it produces an alternating current. And now we have, by Faraday's law, the voltage generated by a AC generator can be given by this equation over here. But let's see how we get to that equation. So we have Faraday's law. First let's define our equation for flux. So we said that our flux is given by NBA cos theta. Or just let's take it as BA cos theta. In this case, let's just assume there's one coil. Or just let's take the flux for a singular coil. Then we have our formula for our induced EMF by Faraday's law, which states that it's minus the number of coils times the rate of change of flux, right? Well, we know the rate of change is essentially the same as taking the derivative of something. So we basically have our motional EMF, or we can write it as our voltage equals to minus n times d, not d theta, sorry, d flux over dt, or d time. Now we know that theta equals to angular frequency, omega, times time. So let's substitute that into our flux equation. We have flux equals to BA cos of angular frequency times time, which means our voltage will equal to, the voltage by AC generator will be the number of coils times the derivative of this, which is minus omega magnetic field strength cross-sectional area sine of angular frequency times time, which simplifies to n angular velocity frequency or angular velocity times magnetic field strength times cross-sectional area times sine of omega t. And this should be in your data booklet. Let me just check it again. Looks like it's not, but well, you don't necessarily have to remember it, but just be sure that you'll be able to deduce it if they ever ask you in an exam. And also I put this out because it'll help us with what we're about to do later. So now let's go into the power output from an AC generator. So an AC generator, like any other generator, produces energy, so thus it has a power output. Now let's see how we can calculate our power output. I'll let these be over here for now. So we know from chapter 5 that our power equals to voltage times current, right? So now let's try and find out our voltage and current for our AC generator. So we know our voltage equals to n omega BA sine angular frequency times time. And also we know that our maximum voltage, or V0 or VO, our maximum voltage will always happen when our sine, this term over here, is equal to 1, because all of these are pretty much constants. Well, not really constants, it depends on our AC generator, but you could take them to be as constants because they don't really change. If you have an AC generator with 30 coils, let's say, it will always have 30 coils unless you replace it yourself. And if it's spinning with a certain angular velocity, it will remain with that. So we can take our initial voltage to be as that. So we can rewrite our voltage as VO sine of angular frequency times time. Yep. Then now we can make use of that in order to get a term for our current as well. So let's see. So we know voltage equals to current times resistance, right? We know this from chapter 5. And we can rewrite it as current equals to voltage over resistance. So let's input our new expression for voltage over here. We get it as initial voltage times sine of angular frequency times time over resistance. Now using the same logic, we can take the initial or the maximum current, because once again it's going to be when our sine term is equal to 1 is equal to maximum voltage over resistance. And we can make this equal to maximum current times sine of angular frequency times time. And now let's put that back into our power equation, giving us, oops, didn't mean to do that, max current times sine squared of angular frequency times time. And that is the equation to find out the power at any given moment. And we can also take the maximum power, which will always be equal to the maximum voltage times the maximum current. And Well, this is also not in your data booklet, but you should keep it in mind. You may have to make use of it, or you can make use of the RMS method or root mean square method. So because our current and voltage are varying by a sine function, or well, they don't really vary in a linear way. So they vary somewhat like this if you were to graph it out with our current against time or our voltage against time. Because of that, we can't simply just do our max current plus min current over 2 in order to find out the average. Instead, what we have to make use is root mean square or RMS. So our root mean square for current is the maximum current over root 2. And well, actually, let me show you why you have to make use of root mean square. I think that would be better. So let's see by referring to current for now. All right. So using what we had earlier, we can also write I square equals to max current squared times sine squared angular frequency times time. Now our sine squared can be rewritten as this here. Can be rewritten as half of 1 minus cos 2 angular frequency times time using our trigonometry rules, giving us our I squared equals to IO squared over 2 times 1 minus cos of 2 omega t. Now over one cycle, our cosine term will average out to 0. You can check that out because it oscillates like this. That's a cosine function against time. If you take the average of this, it will be 0. So we can take this term to be 0 if we're taking the average of both sides. I squared average equals to IO squared over 2, because that averages out to 0. Initial current is a constant, so you can't really have an average of it, and 2 is also a constant. So now that gives us our average current, or our current RMS, root mean square equals to IO over root 2. You can make use of the same method in order to find out the RMS for voltage. Our voltage RMS is equal to max voltage over root 2. This means our average power will equal to our RMS current times our RMS voltage, which will equal to max current times max voltage over 2. Yep. All right, just checking, sorry. Yep, and that's pretty much what I've written over here. Though I should really write this one as well. Just give me a second, let me just write it down real quick. Yep. Next up, we have transformers. So transformers, what they do pretty much is convert AC voltage from one value to another. Let's see what a transformer looks like first. So transformer includes of a core, a giant core, usually of a soft, that's made of a soft magnet, so it can be partially magnetized. Iron is preferable in this case. And let's say we have a certain type of current that's being inputted, and then there's a coil over here. Oops, I shouldn't have drawn it like that. Let's just say it's coiled around. And you have a set of coils on the other side. And note, transformers only work for AC currents. So the idea is that as our current is constantly alternating, there's a varying magnetic field being produced by this coil over here. So we have a constantly changing magnetic field. And this constantly changing magnetic field is experienced by our secondary coil or our output coil. Now this induces a current in our secondary coil, thus inducing EMF. And now, from what we have learned, our EMF, the induced EMF is in essence proportional to the number of coils. So using that, by making use of this proportionality, we can actually change the voltage that's being carried. So let's say we initially had 240 volts over here, and we had 100 coils. And let's say over here we have 50 coils. So let's try find out what our voltage would be. Let's say that's V out. So our V out over 240, which is our input, will be equal to the number of coils in our secondary or output, that's 50, over the number of coils over here, 100. Which means our V out will be 120. But note, our power is the same, assuming that there's no power loss in any form, because of which our current will also change accordingly. So like let's say there was a current of 2 amperes over here. Our output current over here will have 4 amperes, just so that both of them have the same power. Why do we make use of transformers? Well, you can make use of a transformer in order to bring the voltage down to levels that are safe for usage, or increase the voltage while transmitting electricity. The reason why we do this is if you have a greater voltage, you have a smaller current, because of which you have a smaller power loss in the transmission wires. And that's it for transformers. And in the last part of 11.2, we have rectification. So rectification is a method using which we can convert AC current into DC current. Why do we do that? Well, most of our appliances actually work on DC current, so it kind of is needed. So how does a rectifier do this? Well, rectifiers pretty much make use of a series of diodes or semiconductors in order to direct the current in such a way that it's almost always a direct current at the appliance. Let me try show you an example of a rectifier. So let's first draw out our AC source. It has 2 terminals, negative and positive, even though these alter or change all the time. And now we enter our rectification circuit. And these are our diodes or semiconductors. Oops, didn't mean to draw it like that. Well, what do our diodes or semiconductors do in this case? Well, they allow current to flow only in a single direction. And we make use of that by putting it in a very specific arrangement so that we have current flowing only in a singular direction, entering our appliance that works on direct current. Let's draw a diode over here. And our last diode for our rectification circuit. Yep. And we have this connect back to our source. We have this coming out. Let's say we have a bulb over here that runs on direct current. Well, we want at least a direct output from it. And this connects back over here. This here is a simple rectifier. So let's see how this works. Let's say we have first current coming out from here. It goes over here. Now it enters this bridge. So this over here shows the direction in which the current can flow, which means our current can only go in this direction over here, which means our current cannot come into this bridge. So it heads down over here. So this can flow through over here. Now it can't flow through over here because these currents will always go in this direction. So it goes down over here into our bulb, up over here. It comes over here. Now it actually heads back over here because we have a positive terminal over here and our current came from the positive terminal, so it can't go back over here. It comes down over here and ends back at our source. Now let's look at it in the other direction. Let's say our current is emerging from here now. So it enters in over here, coming through over here. Well, there's no connection over here. This is actually going over like that. It's not on it. Just keep that in mind. So our current has entered over here. It can't go over here because these currents will flow in this direction only. So it goes up over here into here. It can't go over there because our currents will come down, can only go this way. It can't go up, so our current goes down over here instead. Once again into our bulb from the same side, and then it enters over here. It can't go here because we can't end at the same terminal, so it goes up and back to our source. That's how a simple rectifier works. We have current flowing in for only one direction. Then you can also smoothen rectifiers by adding in capacitors. So right now you sort of have your direct current coming in like this. But as you make use of a capacitor, you can smoothen this out. I haven't seen a question that actually asks you to draw out a rectifier or explain a rectifier, but it's still in our syllabus, so I'd say it's important to know how they work, just in case. And that's the end of 11.2. Are there any questions? Anything before I move on to 11.3, the last part of EM induction? Anything? All right, I'll take that as no doubts and just move on to the last part, which is capacitance or capacitors. So what is a capacitor? A capacitor is a device that stores electric charge. It usually consists of two plates parallelly placed to each other with a medium in between, sort of something like this. You have two plates, you have negative charge in one and positive charge in another, sort of like our two-plate electric field. Next we have capacitance. So capacitance is a constant for any capacitor, and the capacitance is the charge per unit voltage stored. Our capacitance equals to Q over V. And the unit for a capacitor is a farad. It was named after Michael Faraday. And for parallel plate capacitors, you can also give it as epsilon area over distance. So epsilon is the permittivity of the medium that's between the capacitor, or what's known as a dielectric. A is the cross-sectional area of a capacitor, or the surface area, and D is the distance between the two plates. Usually the permittivity of the medium is given in the question, but in most cases they assume it's the permittivity of vacuum, which is once again epsilon naught. It's a constant given in your data booklet, and that equals to 8 times, sorry, not 8 times, it equals to 8.85 times 10 to the minus 12 farads per meter. So that's capacitance. Next we have discharging of a capacitor. So when you put a capacitor into a circuit, it will automatically discharge because of the potential difference that's there between the two plates. And when they discharge, the charge and the voltage of the capacitor will decrease exponentially. So you have an exponential decay in this case. And using that, we have similar formulas to what you have in chapter 7 or chapter 12. So you have our voltage equals to initial voltage times e to the power of t over tau. So when our capacitor is being discharged, tau over here is the time constant or a decay constant. And tau is given by ln of 2, sorry, wait, hold on, is given by t half-life, or the time taken for half of the voltage to discharge, or half of the charge to be discharged, over ln 2. And it also equals to the resistance of the circuit you've put it in times the capacitance of the capacitor. That's what our tau equals to. Let me write down the one for charge as well. This is the rate at which the charge decreases. Also, there's one more thing that gets commonly asked, and I've seen it appear a bunch of times in past papers. So let's say we have two capacitors over here. All right, they're joined in a circuit, and both of them have a different amount of charge and voltage. All right. Let's say it has charge Q1 and it has a voltage of V1. This has a charge of Q2 and the voltage of V2. Whenever you get such a case, you should know that these charges are going to distribute out in such a way that the voltage of our first capacitor will equal to the voltage of the second capacitor. what is essentially trying to happen over here is that our potential difference is trying to level out so that we have no potential difference, thus no current moving through. And our charge will distribute out into either of the capacitors in order to achieve this over here. Yeah, and actually I should show an example for how we can see our RC. Let's say we have a capacitor connected to a resistor with the resistance of R. So the capacitance of this times the resistance of the resistor it's attached to, or if it's a circuit with multiple resistors, you have to use the total resistance formula from chapter 5 in order to find out what the total resistance is, and then get R tau. Then you can calculate either the decay in voltage or charge. Now, what if you have multiple capacitors? How does that affect the total capacitance? Well, the interesting thing is, capacitors act the opposite way of our resistance does. So if you have a parallel set of capacitors, let's draw out a parallel set of capacitors. Yeah, and the sign for capacitors, both the lines must be of the exact same length. Otherwise, it will be a cell, not a capacitor. Though you can use capacitors as cells, you need to make a difference in this case. Let's say we have like this. If you want to calculate the total capacitance for this capacitors in parallel, let's say this has a capacitance of C1, this has a capacitance of C2. It's going to be just the sum of the capacitors that are in parallel, and so on. Now if you have capacitors in series, say it's C1, sorry, that looks like a G. Let's say C1, C2, our total capacitance over here will equal to, actually let me write it out in a different way, 1 over our total capacitance, 1 over C1 plus 1 over C2, and depending on how many you have in series. Basically the exact opposite of what we did in case of resistors. Next up, you have the energy stored in a capacitor. Energy stored in a capacitor can be given by the equation of half CV squared, or it can also be given as half QV, well, using C equals to Q over V. That's for the energy stored in a capacitor. Yep, I've gone through decay. And like I said, adding a capacitor into a rectifier can help smoothen the output. So rather than getting this haphazard kind of output that you would normally if you make use of a rectifier, you get something that looks a little more like this. Where that's, let's say that's the axis, that's our voltage, and that's our time. If you add a capacitor in parallel, you'll get such an output. And that's all for chapter 11. And that's the end of chapter 11.3 as well. Before I close today's session, any questions, anything you'd like to ask related to this topic? going back to rectifier, what was the one thing in the diagram? Not sure what one thing you're talking about. Were you referring to the source? Was it this? Is this what you're talking about? Amane? Not the source, but the other one. These? Oh yeah, my rectification circuit included of the AC source, the diodes, the semiconductors, which are these over here, and a resistor, or actually in this case I made use of a bulb. Taking a bulb as an example, that's a symbol that's used for bulb. Or, well, it's the same as doing this. Sorry, I used a little more old-fashioned symbol. Sorry about that. Alright, cool. In that case, I'll close for today. I hope this session helped you. And I'll be putting all the stuff up on the revision website soon.